LA?
First cycle. Was painful.
Okay, so last time we had formulated the equations. I didn't put them up there because we did them last time. The idea was that we considered the Earth to be nice and symmetric, a point of attraction O, and then we took a particle of mass m and projected with some initial velocity v naught. Okay? This is supposed to be the Earth, so the radius maybe is r. Okay? And the idea was to contrast two solutions. One considered the uniform gravity field, which is the elemental radial force is always mg. Okay? But what we found out that no matter how high the initial speed v0 is, it's always going to return. Okay? But we found that for the inverse square field, there was this thing called the escape velocity, and if it reached that minimum velocity, actually it keeps going and going, and that's how we actually launch, satellites, etc. Okay? So let's do some numbers. Okay? So for the Earth, we have a radius of approximately 6371 kilometers. That's the equatorial radius. The radius. The Earth is not really a sphere. Okay? And the g is the famous 9.81 meters per second squared. And we had a formula, I think it was the square root of 2rg or something like that. If you look back in the notes. For the escape velocity, in this case, would be 11.18 kilometers per second. Okay? So I'm going to do kind of two experiments. I'm going to first give an initial velocity less than the escape velocity. We know what happens, but let's actually look at the numbers and look at some plots. Okay? Let's choose our initial velocity to be 6 kilometers per second. That's certainly less than the escape velocity of 11, right? And if you work out the numbers in the uniform gravity field, you'll reach a maximum distance from the center of the Earth of 8206 kilometers at approximately 10.2 minutes. And of course, it's in a conservative field, so it hits the ground just in double that time, right? 20.4 minutes. Now let's look at the inverse square field. Okay, you can derive based on the formulas that we had the last time that the maximum altitude is given by this expression. Remember, VE is the escape velocity, V0 is the initial velocity, and for the numbers that I put up over there, it reaches a maximum altitude of 8948 kilometers at t equals 16 minutes. Compare that over here, right? Here, the maximum y was 8206. This is much higher. Why is that? Because as the thing goes up now, this model is recognizing the fact that the attraction of the Earth drops off as 1 over the square of the distance. So clearly it's going to go higher, and it'll go longer, hence 16.1 minutes as opposed to 10.2 minutes. And of course, it'll hit the ground much later, 32 minutes as opposed to 20.4 minutes. Okay, so let's look at some graphs of that. Okay.
For the V naught at 6 kilometers per second,
Yeah.
how long is that going on for? Is that how long is it accelerating for? Is it just a quick force?
No, that's
Shoot it
the
up?
initial. That's initial condition.
That's just
Initial condition. And now gravity takes over.
Okay.
So what's going to happen is that it's going to go 6, and you'll see the plot. It's going to diminish as it goes up, in both cases, right? The thing is that it diminishes at a smaller rate when it's the inverse square field. So, this will work out. Okay, so the first plot is, let me just make it smaller. Okay, so we have time on this axis, I think it's in minutes, yeah. Let me just see. Time in minutes, okay? And this is the case that I just talked about, V0 less than VE, okay? We gave it, I forgot what the number was already, okay? But here's the position, and the uniform gravity field is the blue curve, and the other one, red or whatever you want to call it, is the inverse square field. And notice basically that they're pretty close for the first 5 minutes. Now we see a deviation, is what's happening, okay? The uniform gravity field reaches that maximum height, right? And it's going to come down, and that number is pretty much what I had calculated, okay? And the other one, because it's inverse square field, as we said, it's going to reach a higher altitude, okay, between whatever the number is, it's on the graph here also, around 8,600 or something like that. And of course, it comes down much later. Okay, so that's your position graphs, okay, for the case where V0 is less than VE. And we might as well just look at the velocities also. Okay, so there's your velocity, okay? Okay, we both start at 6 kilometers per second, and you notice that the velocity starts to deviate even before the position does, okay? And of course what happens is that when it hits 0 over here, that's where it hit its apex, right? And now it's coming down, so the velocity is negative, okay? And you can see what's interesting also is that if you look carefully, the blue curve, the velocity looks linear. Well, it is, because its acceleration is a constant, right? So you integrate that, velocity is linear. Over here, you see this a curvature to it, okay? The velocity profile is not linear, although it is decreasing, okay? And I guess I did it till 30 minutes over here. That's when this thing hit the ground, and this one hit the ground, whatever that number is, 16 something. Okay. Now let's do the case where V0 is greater than VE. Let's look at those numbers. Go back to the plot. Case 2, V0 greater than VE. Okay, what was the escape velocity? 11.18. So let's make it 15 kilometers per second. Okay? Uniform gravity field, you can calculate that it reaches a maximum Y of 17,839 kilometers at 25.5 minutes. Okay? And why did I write down anything for the other case? Because it's going to keep on going, right? It's just going to keep climbing, climbing, and climbing. Okay? So let's look at the position and velocity for that case. Okay, V0 greater than VE position. Okay. Yeah, here it is, right? They both start off, of course, at whatever the, y equals r, which is the radius of the Earth, right? And then again, notice how the uniform gravity field of position reaches its maximum altitude and then comes down, okay? This guy just keeps climbing. I had to cut it off over there because of the scaling, okay? But basically, this thing just keeps going up and up and up. It looks linear, but it really isn't, okay? It's because it's, the graphics distorts it a little, okay? So here we see, as far as position goes, maybe you're good for 10 minutes. And of course, the end result is completely different, right? The uniform gravity field, even though we're at an initial velocity greater than the escape velocity, it's going to come down, eventually hitting the ground. And this guy never does, just keeps going. Okay, so it reaches orbit, as they say. Okay, and just to top it off, let's look for the case 2, where V0 is greater than VE. Let's look at the velocity plots.
Does the uniform field assume it's just a constantly extending uniform field?
Yeah, that was the whole idea. F equals mg, no matter how far high you go. That was the whole idea of the study, okay? And now, of course, you've got the velocities. Okay, where's the uniform gravity field? That's this guy, sure. Okay, at t equal to 0, that's when it had that 15 point whatever it was, kilometers per second, and it just keeps going, decreasing, okay? I didn't go all the way where, dy q will become negative after a while, right? This graph really goes down, right, until it hits the ground, okay? But again, just look for the first 14 minutes and you see a huge difference, right? Matter of fact, they start to deviate a bit after about probably 2 minutes, right? This guy basically is just going down. This guy does come down, but it actually just keeps asymptotes to 0. If I were to continue this for time going, it would basically actually would asymptote to this axis, but very slow. The scale, maybe I should take different numbers, but basically this thing does asymptote to y dy dt equals 0. So that's how we got the escape velocity. Remember, we set y to infinity and let dy dt go to 0. Okay, any questions on this? I think this was an interesting problem. Okay, and again, something which to analyze, you had to know how to solve a nonlinear differential equation, at least for the inverse square field. Okay. So let's now, yes, oh boy, there's a lot of people here, so I'll just call out the names and just get your paper, okay? And again, I'll explain very carefully how the points were allocated. So, just for your information, the average was 7.